thought section 2 was generally pretty readable. Couple things came up. One is at the bottom of page 297, they talk about a torus, and they talk about a 1-1 cycle and a 2-1 cycle. I don't know what a 1-1 cycle and a 2-1 cycle are. There's just some things in published papers that you read any paper, you're probably not going to get 100% of it. I just finished my second year of my PhD. I'm pretty confident I could finish my whole PhD, work as a postdoc for 2 or 3 years, read this paper again, and still not know 100% of everything in it, and that's fine. In this case, the 1-1 cycle and the 2-1 cycle never even come up again, so it's totally fine. I will talk about a torus. That's a thing from topology. It's basically a donut. So in topology, you don't care about everything's Play-Doh. So you do care if you break stuff apart, but you don't care about stretching or shrinking things. So basically what ends up happening is you only care about the number of holes. So there's this joke that a mathematician can't tell the difference between a donut and a coffee cup. Why is that? Well, a donut, I don't have a donut here, but it has 1 hole. Here's a coffee cup, I do have that here. And if you look like on the inside, this is not really a hole. Like I could shrink this into a pancake or a ball, or just make it continuous with a handle, and like you could make a ring out of this. So the only thing topologists care about this coffee cup is this hole right here, because if I'm allowed to stretch and shrink, that's the only thing that stays. We can look at a representation of a torus on paper as well. So in topology, a lot of times we draw a square. So here's a square. And then to make a donut, or we only care about the surface of the donut, we don't care about the inside. So to make that, what we're going to do, actually imagine this is a lot longer, and this will be easier. And you can actually do this with a long piece of paper you can tape together. So what you're going to do is tape together the top edge and the bottom edge. So actually you'll like roll it and form a tube. Is what would happen if you had this cut out and you actually did this. And then you'll tape along this edge and this edge. So you'll make your tube, and then you'll make the ends come together, and that will form a donut. There's other fun things you can do in topology. You can look these up, but like for example, you could do this. What this says is make your tube and then somehow tape the other thing, tape the circle instead of normally, so this forms a torus or a donut, tape it the other way. This ends up forming what we call a Klein bottle. Look up what that is. You actually can't realize this in 3-dimensional space. You need 4-dimensional space. But there are 3-dimensional models you can buy. They're kind of pretty. If you have a math nerd in your life that you need a gift for, this is a good option. We don't really care about that. Just to show you what a torus is. This kind of shows you a little bit about what they're talking about with wrapping around with the cycles. You don't have to, there's nothing super concrete to understand here, but just to have these ideas in mind. The other thing to talk about from this section is modular arithmetic. You may or may not have been exposed to this, but they mention mod n at some point, and this means only care about the remainder when dividing by n. In case you haven't thought about anything like this since, 4th grade or something, you took this number 17 divided by 3, we said it was 5, then we're doing long division. 5 times 3 is 15, subtract, we get 2, and then 2 is smaller than 3, so we can't go anymore. We don't know what decimals are yet, so you say 5, remainder 2, and this remainder 2 is what we care about. So for example, if we looked in mod 3, then we would say 17 equals, and then what ends up happening is you can add and subtract 3 as many times as you want. So let's say we add 3, 20. 17 equals 20 in mod 3. Some people write congruent too as well, because both 17 and 20, when divided by 3, have a remainder of 2. They have the same remainder. So, you know, you can say a lot of things. 17 equals 20 equals 11. That's subtracting 3 twice. Equals, and then 2 is the important one. It's a lot, 17, converting 17 to 20 isn't very useful. Converting 17 to 2 is very useful in modular arithmetic. So for the most part in Mod 3, we're trying to represent all numbers as 0, 1, or 2. That's the easy thing to write their remainder as. Something later in the paper, they talk about Mod 1. So usually in modular arithmetic, we're talking about integers. But occasionally a paper will reference Mod 1, and that's not integers. Usually that's real numbers. And what they mean Mod 1, it's the same idea, remainder when divided by 1. So, you know, if you took 1.72 mod 1, what we care about this is 0.72. So it's the decimal portion. And that way you can take all the real numbers and represent them on the interval from 0 to 1. Just for fun, let's say like pi mod 1 is just going to be the decimal part. So not 3, but 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, 3, and so on. I didn't look that up. I have that many digits memorized, but it does go on forever.